Hey, what's up? This is Mark at alchemist.camp, where we learn Elixir and Phoenix by building things. Today we are going to do another episode on protocols. If you watched the last couple, we've just gone through implementing an animal protocol. We covered fallback to any, we covered def delegate, and we also covered derive. And we ended up implementing cats, dogs, ducks, and snails using this animal protocol. If you're not used to protocols, I would say if you've only used them but you've never implemented one, definitely go back and check out that episode, because today we're making a new module and we're going to implement the we're going to implement the Enumerable Protocol, which will give our new module access to everything in Enum, which is pretty impressive because Enum has all of these functions. You can see me scrolling down page after page, and in order to get those, all we need to do is implement 4 functions. Actually, we only need 3 because slice can be implemented by default. We can just pass an error and it will figure it out from the reduce. So let's have a look at our new structure. This is a binary tree. You can see a binary tree is pretty simple. Each one's got a left node, a right node, and a value. I'm using numbers for values just in this example, but they could be whatever. And the left and right nodes are either nil or they're an entire tree. As you can see in this case, this left node is nil, the right one is a tree, and actually this entire tree here is itself the left node of this bigger tree. So we have a binary tree that's 3 levels deep here. This isn't a completely obvious choice of a structure to implement enumerable on, but as we'll see later, it is still useful to be able to use map and reduce and to see if something is a member of the tree or not, and to get a random element of the tree. You can actually do a lot. So let's have a look at our new file for binary trees. Module definition itself will be extremely simple. We're basically just going to define a structure. So our btree is going to have a def struct, and we'll have left default value of nil, right default value of nil, and value default value also of nil. Def impl of enumerable for btree do, so we need to define reduce, count, member, and slice. We'll start with slice since we could skip that one. So slice, whatever is passed in, we're just going to return a tuple with an error and the module. And let's look at the docs again and see what we need for the rest. So count needs to return a tuple with either OK and a non-negative integer or an error and a module. And actually, this is probably going to be easier to implement once we have reduce done. The same is true of member, so let's start with reduce. So reduce is kind of a pain. Let me bump up the font size a bit. All right, so reduce is a little bit of a pain. This is not quite the same as what we're used to seeing in the enum module when we use reduce. It has to apply a reducer, and there's a result and accumulator type. Let's look at this example for reducing lists. It looks similar. We have a list at the front, and we have something in the middle, and then we have a function. However, what's in the middle is not just an accumulator, but we have a tuple. It has the accumulator in the second position, and the first position is an atom that says the status. The reason for this is because streams are implemented with enumerable, and sometimes streams can be halted or suspended. So basically, if we get a halt, whatever was passed in with whatever function just returns a tuple with halted and the accumulator. If it's suspended, then suspended atom is returned along with the accumulator and an anonymous function with reduce, and then actually the exact same list that was passed in and the same argument and the function. Suspend is not always implemented. This is used fairly rarely according to the documentation. Then once you're reducing an empty list, then the whole thing is done. So you have to return a done, and then this is more the normal case of reducing, and we return, or we take a continue and an accumulator and a function, and then we return, and this is just breaking the head off of the list and going through one more iteration. Obviously, this logic is not going to be exactly the same since we've got a non-list. So maybe we should look at some other implementations. Let's see maps. The implementations for built-in types are usually inside the same file as the def protocol itself. So we'll just search for :map. There we go. So here we can see count returns map size of the map. Member does a match with the key and the value. That makes sense. Reduce uses reduced list, and then it's using an Erlang function to turn the map into a list. So this is actually not super useful for us. This implementation is almost the same. All right, so our tree is a little bit more complicated than a list, but let's just copy in the definitions we had from the list and see if we can compare and figure out how this will work. So the simplest case for the list is actually the empty list. In that case, we return done. So if we're reducing down a tree, once we got to where we were at the bottom, say here, we're just looking at the left of this branch here. It's a nil. So that should be the same kind of deal. So if we get down to a nil, we can just return done and an accumulator. Then with a tree, we have one more level of complexity. So we might have a situation where we have either a left and a nil right, or a tree on the right side and a nil on the left side. And in that case, our reduce is going to look something like this, where we'll be taking a slightly smaller tree, kind of like the tail of a list would be, and then we're applying the function to the head and the accumulator. So in the case of this tree here, where the right side is nil and the left side has a tree, the equivalent of reducing the tail of the list, which is everything except the first item in the list, would actually be this left tree here, because that's all the information that's in this tree, except we're missing the nil right, and we're missing this value. And we'd have to apply the function to this value, although we probably want to apply it to this entire tree structure here, even though that it also includes the left, just so that we can do things like check for exact matches or deduplicate, things like that, and then pass along the function as before. Then in the case where the left and the right sides are both trees, we're actually going to have to do two reduces. We're going to have to reduce on the left side once and store that result, and then reduce on the right side. And that way we've gotten all the information we need. That sounds a little bit abstract and confusing, so let's actually copy this over and we'll just use it as a model to get started. All right, and we'll make this copy comments and just keep them as a reference while we change these to work with trees. So let's see, the halt case is basically the same thing. Yeah, actually the halt will stay exactly the same for trees as it was for lists, because whatever came in got halted. The suspend case, this is going to be a tree instead of a list, and once again the logic is going to be the same, because whatever is being passed in, if it's suspended, return a tuple that says suspended, and we give it the same accumulator and we give it a continuation. And the tree equivalent of an empty list would actually just be a nil. And if we encounter that, we'll return done and the accumulator. Okay, so that's the same. And in the standard situation for a list, we'll have a head and a tail, but the tree is going to be more complicated. In fact, I think it's not going to be a one-line function anymore. We're going to have a tree, and the tree is going to have a left and a right. And we're not going to have to do anything with the value there, but we'll store it, or we'll have access to it by storing the tree itself. And the continuation, this part is all the same. Let me save to get rid of that white space up there. And instead of just being able to do it all in one step, we'll get one accumulator, and that's going to be equal to the function. It's an anonymous function, so I have to use the dot before our parentheses. Function passing in the tree and the accumulator. Then accumulator 2 is going to be equal to reduce left, and accumulator 1 is our new accumulator, and the function is the same. Then finally, we're going to return reduce right. So we're getting the left side of the tree here, getting the right side of the tree here, and our accumulator is accumulator 2. So remember, when you're reducing your way through a list, each time it eats the head of the list, processes it, and then updates the accumulator with that information. So as you apply reduce to a list again and again and again, well, just like the name, it reduces a list from a list of lots of things down to just one thing. Since we've got a tree, our reduce basically has to process the left side and then process the right side. And each time it has to update the accumulator. So we have an accumulator. Once we process the left child of this tree, then we need to store whatever changes happened, whatever this function did, in a second accumulator, and then we reduce the right side. So we process the right child, and whatever changes happen to that accumulator will be reflected the next time through. So it's a two-step process. Unlike the list, we've got a couple more cases besides just the base case and the full case. So let's look at the one where we have a tree, but that tree's left and right branches are both nil. So it'll be function dot tree and accumulator. Then we've got the cases where the left or the right side is nil, but not both. So let's copy this up a couple of more times. So if the left is nil, then we're not going to have this step in it. And we'll just get an accumulator from applying the function once, and then we'll reduce right with that accumulator. And if there is a left but there's no right, then it's going to be the opposite. Then we're going to have this reduce left on the accumulator, and there will be no reduce on the right side. Okay, so let's go over all this now that we've got it again. If we have a nil tree, then we're done. If we have a tree where left is nil and right is nil, we apply the function to the tree and the accumulator. And this could be useful, like say if we have a function where we're just adding up the value of all of these, of all of the values in our tree. So like something that goes through and adds this 1 to 2 to 4 to 5 to 3 and gets you the sum of all of those values. Well, even when you're down here at the bottom and you've just got this tree where left and right are both nil, you'd still want to get that value. You'd still need to apply that function to this tree. So in that case, the function would be return the accumulator plus the tree dot value. So we've got that. Then if there's a left branch, or I mean if there's a right branch but no left, then we still apply the function to the tree, but we have to reduce the right branch afterwards using the new accumulator. Pretty simple. And same deal the other way here. And if we've got a left and a right branch, then we've got to apply the function as always, and then reduce the left side, and then reduce the right side, and we've got to be keeping track of the accumulator as we go through. I suppose just for consistency, there's no reason we couldn't call this accumulator 1 and this accumulator 1 just like we had done above. So you can see we have the original accumulator, then whatever this function spits out, and then whatever the next function spits out. btree.ex, get that started up, and we need to copy in this tree example that we have. Okay, so we have a tree, and right branch of the tree, left branch of the right branch, right branch of the right branch. Okay, looks good. So let's see if we can actually use this enumerable on it. And while we're at it, we can just use that function that I mentioned before. So we'll use the right branch, and enum.reduce, and the function will be starting at 0, and we'll just add up all the values in this right branch. So function of tree and accumulator returns tree.value plus accumulator. And what do we expect? We expect in the right side we should have 9. And we do. Let's try that with the entire tree. 15. Is that reasonable? 3 plus 5 is 8, 12, yes, 15. All right, so we've got enum.reduce, but if we scroll up to when we first started, we did get a warning, count is required and it's not implemented, and member is required and it's not implemented. So let's see how we can do that right now. So we just added everything up by using this reduce. In order to count the number of elements, we do a similar thing. We'll have 0 to start with, and then instead of adding t.value each time, we will just add 1 each time, so that every time we do a reduce, we add 1 to the count. And remember, we do 1 reduce per child node in whatever we're looking at. So 5, is that right? Let's see, we have our main tree, 1, 2, 3, 4. Yep, so main tree plus 4 more is 5. Excellent. So we'll define. So count. Actually, let's check the docs. Count has to return OK, and then the count, or an error. Okay. Reduce, and actually it's not going to be the reduce in this module, because that's for enumerable. It's going to be the enum.reduce, which is implemented because we've implemented the Enumerable Protocol. Reduce tree 0 function whatever accumulator plus 1 and okay. Let's load that up, and bt enum.count 5. Excellent. Two. All right. What's left? We need member. Member also returns OK plus what we're used to returning if we're using enum.member. So OK and the Boolean. To get a member out of this, it's going to be the same kind of deal as a count, except we're going to start with false and we'll reduce from there. Okay, so I think member question mark, and that's also going to take a binary tree. We're going to save that as t, and as well as that, we've got something we're testing it against. Because remember, when we call enum.member, we've got to pass it in both a collection and an item, and it says whether if that item is a member of that collection or not. So we'll just say the item is x, return OK and enum.reduce, and this one is taking the tree, but instead of starting at 0 like count does, this will start at false. We'll just assume that whatever item is not in the collection, and the function will loop over, checking element and the accumulator, and it will return. So once the accumulator is true, so like as we're checking through our collection to see whether if each item is equal to this item we're checking for or not, once we get a yes, then we're done. It's always going to be true. So we'll say accumulator or x equals element. So this way, it starts off at false, and we check the item against the first thing in our collection. If that is false, then we have false or false, so it's going to be false. Then we check false is in our accumulator against the next thing, and so on and so on. At any point where that element is equal to x, then the next time around the accumulator will be true, and then it will always be true because we've got accumulator or something. All right, let's save that and give that a shot as well. Recompile and count, have that. So obviously left should be a member of the entire thing. So enum.member bt.left, and right should be a member of the whole thing, and right.left should be a member of the whole thing. Right should not be a member of left. So we have count, we have member, we have reduce, and we have said that we're not implementing slice. The enum module is actually figuring that out based on our reduce. That means we've got the whole thing. So we should be able to do enum.map. So let's look at our tree again. So there's our tree. Let's do map and look at every single value in our tree. So we'll basically turn our tree into a list. So our tree is just t, and we're going to return t.v, t.value. There we go. How about sort? Actually, sort. So that is everything in our tree sorted. How about a random element in the tree? There we go. Let's do it again. Cool. How about shuffle? Let's check unique. It's the same as it was, which makes sense. Let's make another tree, and we'll say this tree is going to be equal to a binary tree where left is bt.left and right is bt.right, and value is 9. So our new tree here has identical left and right branches. Oh no, it doesn't, because I totally forgot what I was going to do. bt.left. So now we have a tree with 2 identical branches. What happens if we put this through unique? We still have the same whole tree, but now we just have 1 element here instead of 2. And notice that each of these enums are returning lists. That's because of how enum is. And so there could be some strange things that happen if we try to use enum.take or enum.drop. I'll give it a try though. Drop happens if I say drop 2 elements. We do have that list. Let's see, enum.sort will get all of them. So yeah, that is a quick example of implementing the Enum protocol. And even though we don't quite, it's not a perfect match for a tree, there actually are useful things here. Like I can definitely imagine having a tree that you want to be able to use map on, or that you want to be able to check if a member exists. I guess we defined that ourselves. But a bunch of stuff we did not, and we totally got for free. So hope you've enjoyed this episode. Hope you learned something. If so, click the bell on YouTube, click subscribe, and see you on alchemist.camp. Until next time, code on.